Welcome to All You Need to Know About Quantum Computing. Quantum computing is a subject that will probably be quite unfamiliar and maybe a little bit intimidating for most people, which makes it actually a perfect subject for our lecture series, All You Need to Know About, which is a lecture series in which we tackle big scientific subjects in a short lecture. And the idea is that the lecture is accessible to pretty much anyone. When I say our lecture series, I mean Studium Generale, which is in up here. Studium Generale of the Tilburg University. We organize a lot of these events throughout the year. If you're interested in those, then you can check out the Tilburg University website or at SG Tilburg on social media. The lecture for today will be about 45 minutes, and in the end there will be time for a short discussion. We have put everyone in the room on mute, so to keep the time as short as possible and the disruption to a minimum. But if you have any questions throughout the lecture or any comments or anything you'd like to say or ask, please put it in the chat box, so we can. My colleague Peter and I will keep an eye on the chat, and if we see any interesting questions, then we can ask them at the end of the hour. That's all the housekeeping for now, I think. So that leaves me only to introduce our speaker for today, and I'm very happy to announce that our speaker for today is Professor Ronald Hanson. He's one of the foremost experts in the field of quantum technology. He is the Antoni van Leeuwenhoek Professor at the Delft University of Technology. He is also principal researcher at QuTech, the Advanced Research Center for Quantum Computing and Quantum Internet in Delft. He's received numerous prestigious grants and awards for his work, and today he is here to share some insights into the wonderful world of quantum computing with us. So Professor Hanson, the stage is yours.
Okay, thanks very much for the invitation. Very happy to be here at home, but to be virtually here with you. I will start to share my slides and start the slideshow. So if you can confirm that everything is okay. Yep, perfect. Okay, yes, so we're going to talk about quantum computing or quantum technologies in a bit broader sense. Actually, if you would look around, you may actually believe that quantum technology is already omnipresent, right? I mean, if you, for example, look for new web browser, you might find the Firefox Quantum, new, fast, fierce. So, okay, it should do something quantum, it looks like it. If you're doing sports, maybe you want to buy a new racket, maybe you want to have the quantum version. That could be maybe the best one in town. Even if you want to do the dishes, you may find quantum to be the top product to actually get your dirty dishes very clean. So, of course, none of this has to do with quantum technology, what I will talk about. But I think the fact that people use quantum always in a sort of positive way, it's an adjective that's used to indicate some superior quality, right? There's something is possible by adding quantum that is not possible without it. And actually that is not so far off from reality as we will see in this lecture. So you may have heard quantum also in relation to real quantum technology. There's been a lot of attention in the past years. A lot of stuff has happened in the field. And basically what I want to do in this short lecture is to give you an idea of what it actually is, quantum technology. Why we believe it's so important, and at the end I will say a few words about why it's actually relevant for us as a country. So how can we actually benefit from the position that we currently have in this new field? So if we talk about quantum, we first have to talk about the roots of quantum. I'm not going to give a physics lecture here. That's of course not the point, but I do want to give you some sense of where quantum comes from. And what are the key elements that make quantum technology a very interesting and powerful new technology. So let's first go back a bit more than 100 years ago. At that time, there was actually a bit of a crisis in science because we had a few very major questions to which there was no answer known, and they were very, very important questions. So one question, for example, was, why is the sun actually still burning? All right, it was known at that time from, of course, Charles Darwin had this evolution theory, but also geological findings showed that the Earth had to be, quite old, certainly more than a few thousand years old than would be possible for the sun to burn, according to the best known mechanism at that time. So any physical chemical process that was known at that time would only keep the sun burning for 1,000 years or so, which of course was not the case. So why is the thing still burning? And then people were actually looking at light coming from the sun, and they noticed that the light had actually very specific wavelengths. So it was not just, all over the place. It was very, very specific, and it was totally unclear why it had that. And when people started to dive into matter more and more and zoom in, they actually found that stuff is made out of atoms, and atoms consist of a positively charged nucleus, the thing you see in the center, and there are electrons that are surrounding this, and they are negatively charged. And so positive and negative charges attract each other. So why don't these electrons actually bump onto this nucleus? Why doesn't the atom collapse? That was a very big mystery at that time. Actually, if you look at the logo of the Study Society of the Delft physics students, you see that thing on the right. This is really like this old picture. I always tell them they have to change their picture because this is sort of the way physicists looked at atoms 110 years ago. It's not very modern anymore. Of course, an electron is not like a billiard ball floating around a positively charged nucleus. And this is actually what was found out by this great group of people. And we often talk about this time between, say, 1915 and 1930 as the first quantum revolution. It was a time at which many breakthroughs were made, and the rules for calculating the behavior of these individual particles, single atoms, single electrons, single light particles, they were set up by these men. And actually there's only one woman in this picture, Marie Curie, but then again, she's also the only one who has received 2 Nobel Prizes of this whole celebrity set here. For, I guess, all physicists all know this picture. For the non-physicists, of course, you see Albert Einstein here in the middle, and next to it is Lorentz, our Dutch godfather of physics. So, out of these rules for how atoms behaved, electrons behaved, and light behaved, we actually got a lot of very cool and important technology. So you see a picture here on the left of the first transistor that was made in Bell Labs in the 1940s. A transistor, of course, is the workhorse of all information processing technology that we have today. So it's part, of course, of supercomputers, of telephones, but it's basically everywhere. And the fact that the transistor works is based on the idea that electrons are not only particles, but they also can transmit as waves. And this is a purely quantum mechanical phenomenon. On the other side, you see a laser. And lasers are, of course, crucial in the distribution of information across the globe. The internet is built around sending just short pulses of light through optical fibers. And also this phenomenon of lasing, that light can unite itself with such a strong beam, is a purely quantum phenomenon. And it's really another technology of the first quantum revolution. Now, you might think, if you see these pictures and you hear this story, that we're actually already fully exploiting quantum, right? All the possibilities that quantum gives are already in our technology today. But it turns out that this is far from true. So if you go back to this picture, and when we think about the core of quantum theory, there are 2 elements that are good to highlight. And the first element is that of superposition. And superposition it's the idea that quantum particles can, in a sense, do two things or multiple things at once. To contrast this to what we see in everyday life, right? If you see me sitting here on a chair, and while I'm sitting here, I'm not at the same time, sitting in a chair 1 meter apart from me. I'm really in one fixed position. But if we look inside a matter, we look at the smaller quantum particles, for example, electrons, we know that they can be at multiple positions at the same time. And in fact, it turns out that this being at multiple places at the same time is what holds molecules together. So it's actually very fundamental. Another concept that is important to note here is that of entanglement. And that is, crudely said, an instantaneous connection at a distance. And I will say a few more things about this concept of entanglement because it is extremely important for the idea of quantum technologies. Okay, so to explain entanglement, I'm going to introduce two particles, and I need some property of these particles to discuss this idea. And the property I take is the color. So I take one particle that is red, I take another particle that's white. And now if I bring these two particles together and I let them interact in some way, then quantum physics says that the properties of these particles can start to mix. And they mix in a very peculiar way. Namely, they mix in such a way that if I look at only one of the particles, I cannot say what color this particle has. In fact, it doesn't have a color of its own anymore. The only thing that is now defined after this interaction is the color of the particles jointly, and that is still one part red and one part white. But individually, the particles have basically lost their color identity. Now, you may say, okay, that's fine if that happens somewhere inside an atom inside my body. I will never see anything of that. But one of the properties of entanglement is that if you separate then these particles, this entanglement can actually remain. So there's no law in physics that says that if particles are separated by a certain distance, this entanglement bond is broken. And that means that these properties can remain entangled even if they are far apart. Now, of course, at the time that these gentlemen and this one lady that I showed you came up with all these rules, this was really mathematics, right? They wrote down the formulas, and these are things that came out of the formulas, but they were not very concrete. They were just things that happened on paper. But we are in the lucky situation that, especially in the last 1.5 decades, many things have happened that have allowed us to actually look into these phenomena and use them to our advantage. And I'm going to give you one example out of my own research, which has really benefited from, on the one hand, advances in nanotechnology. So what you see here is an electron microscope image of a little piece of diamond. And this diamond is extremely pure. So this is a man-made diamond, and we can currently make diamonds that have, where mistakes in the letters are really separated by millions and millions of atoms. So they're almost perfect materials. Also, the equipment that we use to look at these type of structures has increased tremendously. And also new systems have been discovered. And one of such systems is one that I will say just a few words about. And that is a defect center inside this diamond. So you basically, diamond is made out of carbon atoms. So if you see these little blue balls as carbon atoms, and sometimes a carbon atom is replaced by a nitrogen atom, this green guy. And then sometimes next to a green guy, there's an atom missing. And if this happens, you actually form a trap for electrons. So electrons are trapped here inside the diamond lattice. And it turns out that this is a system that you can very well study because it's very well isolated from the rest of the diamond. And for instance, in this device that I showed you, actually you see here this little half dome that we etched out of the diamond. And we do that actually right on top of one of these trapped electrons. So I just drew it in here because of course you cannot see that on this type of microscope. But actually, if we come in with a light microscope, and so we turn on some light and we zoom in to this position, you get a picture as you see in the top left. You see here this outer rim, right? This sort of shade. This outer rim is this sort of the edge of this dome. And then right in the middle of this dome, you see this very bright spot. And this bright spot, this is light. So single light particles emitted by one single electron that is trapped there. So it's one electron emitting all this light into a microscope. And this is a microscope that these days we can build quite routinely. And in fact, so it's if you come to Delft and you start to study physics in your second year, you do a practicum course where you basically look at single electrons using such a microscope. Now, what we can also do is then control the magnetic properties of these electrons. So an electron behaves a little bit like a magnet. And this little magnet you can then manipulate using microwaves. I will not go into the details of that, but you can change its quantum state to anything that you like. And also you can read it out. So you can actually check if this magnet is pointing up, it's pointing down, just by how much light is coming out of this electron. So how much light it's being emitted. Now with these kind of tricks and some more tricks, we've actually been able to make quantum entangled states in the lab. This picture from about 8 years ago, you see from the skill bar here, PhD student of mine, we have two setups separated by a few meters. And each of these setups, we have a little chip, a diamond chip, and one electron is trapped on these chips. So I just indicated them with these cartoons here. And by using all this equipment on the table, we're actually able to make entangled states between these two electrons separated by a few meters. So this little cartoon that I showed with the red and the white ball, we can actually make inside of the lab. Now 1 year later, we were able to use that entanglement to do teleportation of data. So this is a phenomenon that makes use of the fact that this entanglement is there. It uses the entanglement as a communication channel to take data from one place to the other, whereas the data itself never really travels between these two places. So in that sense, it is teleportation as you know it from Star Trek, but all according to the rules of quantum. And actually, when we talk about this at conferences with other scientists, we never say just teleportation, we always say quantum teleportation to make sure that we all mean the same. So this experiment was actually quite a landmark for my group, and we were fortunate to also get some attention on it in the media. And I want to show you one thing that happened actually when the news of this experiment came out. So on May 30th, 2014, Rob Tripp, the main anchor of the NOS 8 o'clock news, had to explain our experiment to the general public. And as I'm trying to explain now that electrons can be at two places at the same time to you, as you are an interested audience. Rob Tripp had to do this to a sort of semi-interested audience at the 8 o'clock news. So the NOS had a bit of an issue here, but they did something very funny, and maybe those of you who have seen it at the time may remember it, because it has never happened before, and I don't think it will ever happen again. So Rob Tripp started to talk about quantum physics, electrons being at two places at the same time. And while he was talking, he was actually projected at the same time in a different place in the studio. And so there were two Rob Tripps on the screen at the same time. So this is probably one of the highlights in my career so far, that I've made Rob Tripp into a quantum superposition. But actually, at the end of this item, he said something interesting. So after the item was over, he said, the scientists also don't fully understand it themselves, when he was talking about the entanglement and the teleportation. And at first, when my team and I saw this, of course, you were like, I mean, what do you mean we don't understand it ourselves? We've devised the experiment, we know exactly what's going on. Quantum theory exactly predicts what the outcome is, and we've seen it, so we understand it. But maybe Rob Tripp was hinting at something else, because you can ask the question, of course, do you really understand the phenomena of superposition, being in two places at the same time, or the phenomena of entanglement? Is that really something that we intuitively understand? And I think that question has quite a different answer, and it's a question that many famous scientists have asked themselves, and most notably Albert Einstein, probably one of the best physicists we ever had. He talked about spukhafte Fernwirkung in German, a spooky action at a distance. He said this idea that there is a connection at a distance between particles is actually impossible. And he took that idea, the fact that the spooky action could not be, to argue that quantum theory is actually wrong, according to him. So he wrote a paper, very famous among physicists, Einstein, Podolsky, and Rose are the authors, or EPR, we call this the EPR pair, and they wrote this paper in 1935, and the sole purpose of the paper being to basically cut down on quantum mechanics and say the theory is not complete. And interestingly, despite all the breakthroughs that Einstein made, this is his most cited paper up to today. So what did Einstein then say about entanglement? So Einstein said, well, you know, maybe it looks like there is some correlation between these particles, right? If I do my measurement, but maybe these properties were already set before, right? So if I take them apart, I measure on one particle and I get the color red, then the other one, of course, must be white, because we knew there was one part was red, one part was white. If the left one would have turned white, the other one would have turned red. And Einstein says, well, that has nothing to do with entanglement. It's just the fact that quantum theory didn't know that the particle on the left was already red to start with. The theory is incomplete. Now, at that time, this was an academic discussion, and people could not do experiments, of course. But in 2015, we were lucky enough to be in a position to actually test this by taking the distance between these two electrons from a few meters to more than a kilometers. And by doing that, we could actually make sure that there was no way that there could be communication between the particles during the time that we did the measurement. So the idea that, you know, somehow we get correlations because there is something going on between these particles in the meantime was thrown off the table. Now, for physicists, the outcome was not a big surprise, but it still made actually quite some headlines. And I just dug up this New York Times picture, because you can see actually our experiment is discussed here in the lower half. It's me, and so the New York Times said here, sorry Einstein, spooky action seems real, to actually dismiss the objections by Einstein. And I was always very happy that I was on the front page of the New York Times together with an American president, but actually very soon I will have been on the front page of the New York Times with 2 American presidents, because you see that Joe Biden is also in that picture. Okay, but why did the New York Times find it so important? Was it because it overruled Einstein's objection? Well, partly, but also because there is another aspect to this. And this brings us to the idea of quantum outperforming classical technology. So if you would do the experiment that we did on the TU Delft campus, which was more or less a game to get correlations at a distance. So the game was that the higher the correlations between the measurement outcomes, the better. And it turns out that if you do this game with classical ICT, so meaning you just take supercomputers, they can have unlimited classical computing power. You can even have them connected by unlimited bandwidth, although the information cannot should not go faster than the speed of light. So it's bounded by the speed of light, but otherwise unlimited. In this game, you can only get a maximum of 75% score. So that is just a fundamental mathematical limit. And it turns out that if you use this entanglement, you can actually get 85% correct. So by using 2 entangled particles, you can beat the very best of our classical machines in a certain game. Now that's interesting, but it's not only interesting, it actually turns out that this is of practical use. Already in 1991, Arthur Eckert showed that by using this sort of quantum game, you could make a communication channel that is secured by the laws of quantum physics. And the idea behind this is that this entanglement is what we call monogamous. And that means that if 2 particles are maximally entangled with each other, there's no way that a third party can have any information on that state. And what Arthur Eckert showed is that actually using this entanglement, you can distill a private key. So you can use a key that's only known to the the two parties that have these entangled states. And this key you can then use to encode your messages, and it cannot be encrypted because it's a perfectly secure key. Now, the idea then is how do you actually know that you have these entangled states to make these secret keys? And that's where you can use that quantum game, because if you run the quantum game, in some of your trials, and you find that you win in more than 75% of the cases, you have a firm guarantee, a guarantee by the laws of nature, that you have a private channel. Now, in 1991, when Arthur Eckert proposed this, it actually came as quite a surprise to the community that such a fundamental concept as entanglement could be useful. It could be useful in something in the real world. But actually, today we understand that this is part of a much more general class of applications. And to appreciate that, maybe it's good to take a zoomed out look at the information technology that we currently have, right? We've made this transition from the abacus that you see on the left to integrated chips, the internet spanning the world. And of course, they look very different, and there's much progress. But at the heart, the way these devices process information is actually exactly the same, right? In the abacus, there is a marble, it's up or down. In a transistor, the voltage is high or the voltage is low. And the same is true for the internet, where the voltage pulse gives the value of a bit, which is 0 or 1. And the fact that all these machines operate in an analogous way at the fundamental level also means that their speed and functionality is limited in the same way, namely by classical mechanics. Now, I just told you that nature does not work that way, right? In nature, things can happen at the same time. And that also means that the current computers that we have are, in a sense, too simple, or if you would like, they are too stupid to calculate what is happening in nature. And let me give you an example of that. So if I take the world's most powerful supercomputer, the Fukaku computer of Fujitsu, huge computer, amazing computational power. If I want to calculate the chemistry of a rather simple molecule, caffeine molecule, has a bit more than 20 atoms. And when I talk about chemistry, I mean I want to calculate the energy levels of the electrons in this molecule. This most powerful supercomputer can barely do this. So this is a task, like 20-ish atoms, it can just do it. But if I just add a few atoms and make it a little bit larger, make a penicillin, for instance, then already quickly it becomes intractable. And these are very small molecules, right? So if you think about relevant molecules like DNA or certain proteins, if you want to calculate the biochemistry of that, these molecules are thousands to million times bigger than these molecules. It becomes clear that we will never be able to calculate that with the computers that we have today. And I want to give you some intuition of why that is. So the quantum rules say that if I take one atom, right, say this atom has two possible states that it can be in. It can be in the superposition of these two states. So if I want to track what this atom is doing, I need to actually track two numbers. How much is it in 0? How much is it in? If I take two atoms, I have to now track 4 numbers, right? Because it can be in any of these 4 states also at the same time. If I now have 3 atoms, I have to track 8 numbers, and you see where this is going, right? 4 atoms, 60 numbers. This is an exponential law, and that doesn't bode well for the classical computer. And in fact, you can make this more formal. If you have n atoms and you want to track the evolution of n atoms, there's 2 to the power n complex numbers that you have to track. And 2 to the n quickly becomes huge. So if you are about 50 atoms, 2 to the power 50 is about the size of the memory of the largest supercomputer that we have today. If you talk about 500 atoms, still rather small molecule, you're talking about so many numbers. This did 2 to the power 500 is about the number of atoms that there exist in the universe. So even if you could take every atom in the universe and use it to put a number on and to process all that in a machine, then you would still not be able to can calculate what's going on inside a 501 atom molecule. But what if we would now actually mimic nature? What if we actually say, let's not do it this way, but we're going to do it differently. We're going to calculate in the way that nature does itself. We're going to use quantum bits. Quantum bits that cannot be just 0 and 1, but they can be 0 and 1 at the same time. What if we do our calculations and our communication that way? Now, it turns out that in this way, we can not only calculate like nature, but we can also get speed up in solving other relevant computational tasks that are currently really out of our reach. And to give you some intuition of how that then works as a computational power, let's just look at a maze. Say I have my task is to find the way out of this maze. If I'm a classical computer, then I just try one route. If it fails, I just try another route, and if it fails, I try another route. I can just try and try and try and try, and at some point, I will find the route that actually takes me out of the maze, and I will have my solution. So, simply put, the classical computer will serially, one by one, look at all the solutions. A quantum computer, because it can do things at the same time, can probe all the different solutions at the same time. And so it will also find the right solution by probing all these different routes. So it's this sort of parallelism in the computation that actually gives the quantum computer this power, this amazing advantage over classical computation. And so this has a couple of very interesting applications. I think I should start by saying that when we talk about applications, it is unclear at the moment how far these applications go. Right? We are really at the start to try to understand where we can use and apply quantum computation, and the field is still at a very early stage. So it might be much bigger than anything that we can ever possibly imagine, but we know already a few things. So, for example, if you think about batteries, right? We would like to have a battery without loss, or we'd like to be able to transmit energy without loss. Now, it turns out that there is a class of conductors that we call superconductors, and these are conductors that actually transmit current without any losses. The only thing is that in order to use these superconductors, we actually have to cool them down, and the cooling down, of course, costs a lot of energy. Now, we would like to find one of these superconductors that actually works at room temperature. And we know what the calculations that we have to do to understand the properties of these materials. But these calculations are too difficult for the computers that we currently have. So the hope is that once we have quantum computers, we can actually predict and sort of tailor the properties of these materials, and hopefully find a material that is either superconducting at room temperature or at slightly colder temperatures. Another example is in the area of climate. In the process of making fertilizers, there is one step that is extremely inefficient, and that's so inefficient that it actually takes about 3% of the world's energy production today. And it turns out that this particular step, which is called the nitrogen fixation, is a step that a bacteria in a particular plant also does, and the bacteria actually does it very efficiently. But we have no way of understanding how that bacteria is doing that, because the chemistry is too complicated for us to simulate. Now, of course, if we would have a quantum computer, we would not have those troubles. We could actually simulate the energy levels in that chemical process and be able to find a solution that the bacteria has. And that could potentially save a couple of % of the world's energy production. Now, in the area of health, we talked about the ability of quantum computers to simulate molecules, big molecules. Of course, if you look at the effect of medicine in the body, where we're talking about the biochemistry of very large molecules, this is something that is currently, a bit of the trial and error in science. And so, if we would have a large quantum computer, we could actually calculate and predict certain properties of medicine. So the hope is there that we could go from trial and error to, really pre-simulation on a machine without having to test it on animals or humans, and also being more efficiently in finding new methods. Now another area is internet security. We already talked about securing communication channels, and actually by using entanglement, there's a level of privacy that you cannot attain, that you can fundamentally not attain in the internet that we have today. So you can also think about, for example, privacy in online auctions, online elections, and so on. So there, the internet security domain is definitely a big application area. Now, as I said, there's a lot of research going on where can we use quantum technologies in the different types of areas, and there's work going on in financial services, links to artificial intelligence, optimization problems, many things. And the expectation is that in the next 5 to 10 years we will learn much more about where we can actually use it, and probably there will also be areas where we find out it's actually not useful. So the fog will clear as we go along. So if you think a little bit about timelines, so this is a picture I took from another presentation, and it mentions these different lines of quantum technology. So quantum computing we talked about, and quantum simulation is in a sense a branch of quantum computing. Quantum communication or quantum internet is here, and also quantum sensors are there. And there are some, people have put some milestones for when we could do certain things. The reason I'm showing this slide is because of the time scales on top. So the expectation is that really, if you look at the grand goal, right, a quantum internet that really can connect many users, a universal quantum computer that we can use to calculate really large molecules, etc. These will happen on a timeline of 10, 15 years. And small-scale applications that use maybe smaller machines that are, less advanced can already happen on a shorter time scale. So this is about the timeline of when this technology is expected to really enter society. Now, in 2014, we actually founded a new type of institute to work towards these type of technologies. We call it QuTech. It's a collaboration between the University of Delft and TNO. And what is really unique here is that we brought together all the different disciplines that have to contribute to this field, which is physics, but it's also computer science, electrical engineering. We brought them into one building. So actually the TU Delft and TNO people and also industry collaborators, they're working together really in one building. And what was really nice at that time is that the government said, we see that this is going to be a key enabling technology, and we will fund you with a long time horizon, 10-year base funding, which is quite extraordinary actually for funding cases. And so we're directly funded by the Ministries of Economic Affairs and the Science Ministry. Now today our institute has about 200 researchers, and to give you some idea, turnover is about 30 million a year, of which 1/3 is about private contributions to our research. Now I actually was planning to show you a little video of the lab, but it turns out that the sound doesn't really work when doing that in Zoom. So I'm going to tell you that if you want to see what the labs look like inside, you can actually go to the website that is below the link, or if you just Google QuTech Lab Tour, you can go there. It's on YouTube, and you see here the pre-corona version of me, the time when we were still shaving, and I will guide you then in this little tour around QuTech, and you can actually get a little bit of the feeling of the type of equipment is there. And you see the labs, a little bit of the chips, the electronics, etc. And it actually makes it a bit more tangible than just pictures in a PowerPoint presentation. So please, after this presentation, if you really want to know more, feel free to go there and have a peek. Okay. So finally, in the last minutes, I want to tell you something about what is happening nationally here. because there's not only QuTech in the Netherlands, there's several other institutes that are now really focusing on quantum technologies. There's a quantum software center in Amsterdam, there's a quantum materials center in Eindhoven, for instance, and all these parties are actually now joining forces together, and we have a new entity that we call the Quantum Delta NL Consortium. And its goal is to really build a leading quantum ecosystem, not only advancing the science and technologies, not only technology push, but also to build new companies, train new people, and think about all the other aspects that are important in this field. And we've actually written a national agenda, quantum technologies. You see this here, handed over by Robert Dijkgraaf to our State Secretary Mona Keizer. And what we do is actually these different action lines that you see in this left picture. So it's research and innovation, ecosystem, startups, human capital that I just described. And also we are thinking about ethical, legal, and societal aspects, because quantum technology is likely to be a disruptive technology. And it's very important to already at this moment think about the consequences that this certain technology can have, and also how to embed it into society, right? And we should not wait 10 years and then suddenly the technology is there and we don't know how to use it or to incorporate it in a good and a safe way into the society. So these are these 4 different action lines, and you see on top these little pie pieces. These are catalysis programs that actually push certain technology platforms. So there's one on computing, one on quantum networks or internet, and one on quantum sensors. So this with this technology, we actually, or this agenda, we got an initial funding from the Ministry of Economic Affairs of 23 million early this year, and we're actually hoping that in new considerations that are soon taking place, we will be awarded a substantially larger amount to actually make this agenda happen and to execute the full 7-year time plan that we've written down in this agenda. You can find this agenda also on the internet. If you just Google National Agenda Quantum Technologies, you will find it very quickly. So I think this about ends the 45 minutes. Let me end here and just conclude that the future is quantum, according to me at least. I want to thank you for your attention. I'm very happy to answer any questions and maybe explain a little bit more on certain questions that you may have. Thank you very much.
Okay, thank you. I see that a few, we have about 10 to 15 minutes, as I said. Well, 15, I see. We have a few good questions in the chat. So first of all, I see a question from Nout. Do you have an example of how quantum computing could be used in the financial world?
Yeah, that's a very good question. Actually, the financial world is very interested in quantum. There's several different directions in which people are thinking. One direction is that in treating big data. So if you think about machine learning or searching data for certain anomalies, for example, fraud detection, it is expected that a quantum computer is much more efficient in finding these. So actually, we are currently starting up a couple of projects with the NVB, Nederlandse Vereniging van Banken, Dutch Society of Banks, to look into a few of these cases, where indeed they're mainly based on big data and finding certain patterns in that data. And another direction that the banks are very interested in is in this secure communication. So obviously, if you let me give just one example. If you go to an ATM, which I guess many of us haven't done in a long time, but when we used to go to the ATM, you go there, you take your money out. The machine knows that you've taken some money out of your account, and all the other machines that actually have to know something about your account need to be updated, and they have to be consistent with each other. So there's a task to make the whole system agree on a certain amount on your account. And it turns out that this is one of the problems where a quantum network can actually be more efficient and build in some safety features. So this, of course, is also very interesting for the financial world.
And the question from Caspar kind of fits in here. He says, I was told there could be some serious geopolitical consequences when one country has access to properly functioning quantum computer while other countries don't, especially involving banking and communications.
Yeah.
Yeah, is this something that worries you, and are precautions being taken to implement quantum computing safely once it becomes available?
Yeah, yeah, that's a good point. I think to sharpen it a little bit, I think there would be geopolitical consequences if one country has a very strong, basically full-blown quantum computer, and other countries are not aware of that. They're A, not aware that this first country has it, and B, they have not taken precautions in protecting their very sensitive data. So if that happens, then that is a risk. And why is that a risk? Because there is an algorithm known for quantum computers that can crack the RSA crypto, and that is basically encrypting most of our sensitive data exchange that we have today. So if the RSA is indeed decrypted, then there will be an issue. So what is happening now today is that we have a sense of where quantum computers stand. So there is a sort of a safety margin to where they're going to be in the near future. The gap between the complexity of our encryption and the quantum computer will shrink in the future. So at the moment, the idea is that we just take a safety margin there. At the same time, we are working on different types of encryption protocols that are resistant to this cracking. And this is an area that's called post-quantum cryptography. It's a research field on its own to devise cryptographic schemes that cannot be, at least not easily, cracked by a quantum computer. So that is one path. The other path is actually to use quantum itself to encrypt, right? So one can actually use these properties of entanglement to do an encryption that is that can actually not be cracked by a quantum computer, because it cannot be cracked by anything for the fundamental reasons that I explained. So yeah, so people are well aware of this right now. I mean, I mentioned that we started QuTech in 2014. It was very early. After that, I think 2015, we were already at the ministries to explain to them what was going to happen. And of course, for the super sensitive data, people are looking 20, 30 years ahead, and so they know what's coming. Yes.
A question from Michiel is about another aspect of the quantum technology. He asks, how will the quantum computer help with navigation without GPS? So how does that work?
Yeah, there are ideas. This is not per se quantum computation, but there are ideas to use quantum sensors to do the navigation. This has to do both with the fact that they have a different. No, let's put it differently. They have a sensitivity that can directly sense their position on the globe, and they have a very good internal clock. And that combination might allow you to do this in navigation that was being asked. So it's not really a quantum computing application, but it's really a quantum sensor application. But it is, we see that as part of quantum technologies. Yeah.
Okay, and that's one of the uses of quantum that might make its way into consumer technology. Stijn Kanters asks, what will the main uses of quantum computing be for individual users? So are there any applications for consumer technology that we might see in the next few decades?
Yeah, that's a very interesting question, of course. I think if we could predict that now, we could become very rich, probably, and rich and famous. I mean, when we set up the internet, the classical internet, I don't think many people would expect that one of the main applications would be downloading kind of cat videos. You see, so but okay, if we try to look a little bit into the future, so what does a quantum computer bring compared to what we have now? I mean, if you want to do text processing like Microsoft Word or so, right, you don't need a quantum computer. And there are many other applications where a quantum computer will not really bring you any real advantage. So the quantum computer will be used in those cases where there's a very hard computational problem at stake, and where that will be for individual users, yeah, that I think it will depend on what the users is going to do, but it will typically be in that area. So computations that are really just hard, or have to work on massive amount of data, have to manipulate, search inside a massive amount of data. This is the type of thing where it can make impact. But the big question is whether individual users will ever see that they are using a quantum computer, right? Just like individual users now don't see that they're using a glass fiber that is in the ground, or whether there's a laser at the repeater station for the internet. Nobody. Most people don't have a clue what is behind, they're using their phone and sending a message and getting something back. So actually, my personal expectation is that most individual users, consumers, won't see the quantum computer directly, but they will only see the benefits of it.
And then one more question from Joel. Do you think this technology could influence the hierarchies in which communicative power is ordered? As in, could this give some organizations with the capital to afford such devices an extreme advantage?
Yeah, that's a good question, and this is one of these questions that comes up when you think about how is this technology, or any technology, going to impact society or the world as a whole, and can you, or should we take measures to prevent that you get disadvantages based on access to quantum technology, right? Yeah, so, I mean, this could be between organizations, but also between countries. For instance, like third world countries might be at an extreme disadvantage if they don't have access to quantum technology. So these really go into the realm of societal and ethical questions. The answer, I mean, the answer to this question is, of course, yes. I mean, if one organization or one country has access to a certain technology that is very powerful and another country doesn't, then there is an advantage. And I think then the next question should be, how do we deal with that, and how do we make sure that any advantage or disadvantage is proportional, at least in something along the values and the ethics that we would like. But these are very good questions to pose, and very good questions to start answering, I think, within the next decade.
Yes, because in the Netherlands, you've shown there's a quantum agenda. Is there something international that is being communicated among the big nations who are doing research into quantum technology?
Yeah, so there is a European agenda on this, and actually Europe has what's called a flagship program for quantum technologies. It's an investment of €1 billion over 10 years. Although one should always realize that when the EU is investing 1 billion, then usually it's not the EU investing 1 billion. Also in this case, it's $500 million EU and $500 million has to come from the member states, but still there's a certain big commitment there. And maybe zooming out of quantum, the ideas of digital sovereignty, or technological sovereignty, or economic sovereignty, these are political discussions that are really taking place now, right? Should we, as the Netherlands and Europe in a bigger frame, should we together work on making sure that we at least have access to this technology as a group of countries, and make sure that we don't become dependent on countries that maybe we don't fully trust, or that something could go wrong in the future. So yes, this is very high on the European agenda. and there are also European programs, and they always tie into these national programs. So when you have a national program, you can also better participate in the European programs, and vice versa. So it's not that we wrote this national program and then we say there's a fence around the Netherlands and we're not working together with anyone else. It's of course embedded in the larger political structures. Yeah.
Okay. Well, I think we've discussed all of the questions in the chat. I have one last question. If our viewers today want to get more invested in the topic, if we want to get more knowledge on quantum computing, do you have any reading tips or any websites that we can visit to study up a little bit?
Yeah. So at QuTech, we have a branch that's called the QuTech Academy, and there we have so different courses, but also just videos, explanatory text and videos for different levels. So people that don't know anything about it, people that work in business, or really students that want to understand the technology behind it. Maybe if I can if I stop share, maybe I can actually put it in the. I quickly find the link and I can just put it in the chat. Actually, this is the website of the national consortium, if you want to understand a little bit what's going on. And then maybe a book at layman level about sort of introductory. It tells you something about quantum and quantum computers, but
okay, perfect for everyone's wish list this Christmas. Okay, well, thank you very much. I think that's all we have time for. Thanks for your time. Thanks everyone for watching. Remember to also check out Studium Generale on the Tilburg University website and on social media. And yeah, I hope to see you next time. Goodbye.